Hello everyone, this is Dr. T. Bhargava Ramu, Assistant Professor, EEE, MLR Institute of Technology. So, we are discussing regarding underground cables which comes under power system topic. In last class, in last video, we have discussed regarding overhead transmission line and underground cables difference, and what are the merits and demerits, and what are the insulating materials generally we use for underground cables, and types of cables we have discussed, and materials utilized for insulation also. So, in today's topic we will discuss regarding some parameters related to the underground cables. So, parameters in the sense, generally overhead transmission lines consist a resistance parameter, an inductance parameter and a capacitance parameter. So, these three parameters we will study in case of overhead transmission lines. Similarly, in case of underground cables also we have some parameters need to know. So, that is, insulation resistance, as we discussed in previous video, underground cable consists an insulation over it. That insulation resistance we need to know, so that we can know the power carrying capacity of the underground cable. In addition to that, an underground cable consists capacitance also. An underground cable consists capacitance parameter also. That also we need to know. So, how much value capacitance will exist in case of underground cable. And one more parameter in case of underground cable, that is dielectric stress. So, this is also one of the important parameter in case of underground cables. So, mainly insulation resistance and capacitance and dielectric stress. These three parameters we need to know in case of underground cables, and RLC, these are the parameters we will discuss in case of overhead transmission line. So, in today's lecture, we will discuss regarding resistance and capacitance and dielectric strength of the underground cable. If you see, the diagram is showing that an underground cable. So, this is the cross section of the underground cable. So, that cable is having a length L length L it is having, it may be in meters or kilometers like that. So, L lengths, for analysis purpose we have taken length L, and moreover in the middle of the underground cable we have taken, it is represented as conductor, copper conductor or aluminum conductor is placed within the underground cable, and over it we have taken the radius of this conductor is R, radius of this conductor is taken as R, and the total radius of the cable is taken as capital R. So, small r represents radius of the conductor which is placed within the underground cable, and R represents the radius of the total cable. And in this, generally analysis, how analysis we will take is, so we will consider an within the conductor, within the underground cable, we will take a elemental strip, dx, we will take dx strip, so which is within the underground cable. So, by taking that elemental strip as shown in this figure, just you can see. So, within this, you can say this is a cross section view of the underground cable. Within this we have taken a dx length, that is already also we can represent it as delta x also. That elemental strip is represented with delta x or dx we can represent. So, that small r is the radius of the conductor and capital R is the total radius of the underground cable. So, if we know generally for a conductor resistance value is given by rho L by A. Rho L by A. So L is the length of the conductor, A is the cross sectional area of the conductor, and rho is the permittivity of the conductor. So like this, by considering this kind of formula, if you integrate this value for dx length, if you integrate this with r to r, small r to capital R, so it is shown here small r to capital R, small r to capital R, if you integrate that same formula, finally we will get total resistance of the underground cable as shown in the figure. So this figure is showing as same like previous figure. So finally we will get, after integrating, so resistance of the conductor is rho by 2 pi L ln means log base C capital R by small r ohm. So by using this formula we can calculate the total resistance of the conductor. Here rho is represented as insulation resistivity, that is dielectric resistivity in ohm meter. Units of this rho is ohm meter. So Ri represents insulation resistance in ohms. So what we have done in case of calculating the resistance, so we have taken an elemental strip of the conductor of the underground cable. Okay, so that elemental strip resistance value is taken as rho L by A. Is rho L by A. So A value is replaced with cross sectional area of that strip, right? And that value is integrated from small r to capital R. So finally we will get this formula. This formula gives insulation resistance of the cable for length L. So rho is the insulation resistivity and L is the length of the cable, and capital R is the radius of the cable, and R is the radius of the conductor. So we can observe that by using this formula, we can say insulation resistance of a cable is inversely proportional to its length. Resistance of the cable is inversely proportional to the length. If you take long length cable, resistance value will be less than short length cable. So R is inversely proportional to 1 by L. So this is one of the observation we can see from this formula. So coming to next parameter, that is capacitance parameter of a cable. So in previous discussion also we have taken single core cable. Here also we are considering a single core cable. So generally potential difference will be there between conductor and the sheath. So sheath means the outer surface of the underground cable. This outer surface of the underground cable is called as sheath. It will have sheath. So between this and between the conductor, so between these two, so conductor will be at the middle of the cable and sheath will be outer. So between these two, potential difference will be there. So that potential difference is given as Q by 2 pi epsilon ln d by d. So here in this figure we considered capital D is the diameter of the total underground cable, and small d is the diameter of the conductor within it. So D means, capital D means total diameter of the cable, and small d means diameter of the conductor which is placed within the underground cable. So voltage difference between conductor and sheath is given as V, which is represented by Q by 2 pi epsilon ln d by d. So Q is the charge on the conductor. And we can replace epsilon as epsilon naught into epsilon r. Epsilon naught is permittivity of the free space. We know 8.854 into the power of minus 12 farad per meter. Permittivity of the free space. Epsilon r is relative permittivity of the insulation. So relative permittivity, generally we don't have any units for that relative permittivity, because it is epsilon by epsilon value, we will take it as relative permittivity. As we said, Q is the charge per meter axial length of the underground cable. That means Q means if you take a 1 meter length of the conductor, the charge on the conductor is taken as Q. So coming to, so for capacitance calculation, we know C equal to Q by V, this formula, C equal to Q by V. So if you want to calculate C, we need to divide Q with V. So in previous formula, voltage formula, so if you convert this as a C equal to Q by V, so V comes here and 2 pi epsilon go that side. So finally you will get capacitance value like this, 2 pi epsilon by ln d by d farad per meter. 2 pi epsilon ln d by d farad per meter. So this is one more parameter which is related to underground cable. Coming to next, dielectric stress of a single core cable. So this is one more parameter which we need in case of underground cable, dielectric stress. Under operating conditions, the insulation of the cable is subjected to electrostatic stresses. If you keep on operate the underground cable for power carrying purpose, the cable undergoes electrostatic stresses. That electrostatic stress is called dielectric stress. That electrostatic stress is called dielectric stress. The potential gradient at any point is defined as the rate of increase of potential at that point. So generally this discussion comes in electromagnetic field subject also. So potential gradient means electric field intensity, we can call it as electric field intensity also in case of electromagnetic fields. So that potential gradient at any point is defined as the rate of change of increasing of potential at that point. Some which leads which we can say that value we can say as it is dielectric stress also at that point, at a particular point. That means if you consider from the center of the conductor underground cable to at a particular point, if you consider this is an underground cable from center to a particular point, if we calculate potential gradient between this point to up to this point, so that potential gradient is called as dielectric stress at this point P from O. If we calculate potential gradient from O to P, that value is called dielectric stress at point P. Since cable is a form of cylindrical condenser, therefore electric intensity at any distance x from the center of the O cable is given by the following formula. So this is, we can say this formula from electromagnetic fields, we can have this relation, electric stress at a point x from the center of the cylinder, is given by 2 pi epsilon 1 by x. That means if a cylindrical shape carrying conductor is there from the center to a point P, okay, if a distance x is there, so at a point P electric field intensity is given as q by 2 pi epsilon naught 1 by x. So the same electric field intensity is we can call it as potential gradient. This potential gradient in turn we are calling it as electrostatic stress at that point P. So now Ex is represented with stress G, potential gradient G, the same formula q by 2 pi epsilon 1 by x. So we know that from capacitance formula V is q by 2 pi epsilon ln d by d, just now we have seen. So by incorporating these two formulas 1 and 2, this one and this one, G and V, so finally we will get the electric potential gradient at point P. G is given by V by x ln d by d. So if we club G and V, these two formulas, finally we will get G equal V by x ln d by d. So and one more thing is the dielectric stress variation. So potential gradient will be maximum when x equal d by 2. So if you consider a round conductor, if x value is nearly which is called d by 2, small d by 2, that means small d is diameter of the conductor, which is potential gradient is maximum when x value is equal to d by 2. That means over the conductor gradient will be more, x will be G value will be more. Potential gradient will be minimum at x equal d by 2. That means d by 2 means this is d by 2, this is capital D by 2, this is small d by 2. If you go on moving from here to this outer surface of the underground cable, the G value will slowly decreases. At this point G will be minimum and over the conductor G will be maximum. So that is the difference between G value from center of the underground cable to the edging of the underground cable. And G maximum, G minimum formulas are given here. These two formulas hold good for maximum by minimum values. If you take the ratio of the maximum and minimum, so you can say you will get it as D by D. D is the diameter of the underground cable, small d is the diameter of the conductor within it. So if you see the most economical diameter of the conductor, so for any cable we should have a limit. Otherwise, so if you take a small thin conductor and over it if you take maximum number insulation area, so you won't find economical. So for economical purpose, for given operating voltage and given overall diameter, the conductor which gives minimum potential at the surface is the most economical diameter of the conductor. That means, so D value should be, small d value should be equal to capital D by 2.78, D equal to capital D by 2.78, 718. So if we follow this ratio, that means conductor diameter is suppose let it be 1 centimeter. So based on that, how much underground cable diameter should be there. So like that we have to calculate and we have to take the sizes. Otherwise economical conductor we cannot make it. So for a given applied voltage, electrostatic stress in a single core cable is maximum at the conductor surface and it decreases towards the sheath. So as we discussed, the same point it is telling. So the electrostatic stress will slowly decreases if you reach the sheath area from the conductor area. Next, so the G maximum at the surface of the conductor, G minimum at the surface of the sheath, this implies the unequal stress distribution in the cable. So that means as we discussed, so G value will change from center to the surface. That means if you go on moving from center to the surface of the conductor, surface of the cable, the G value will vary, but this variation G is not suggestible. So this variation of G is not suggestible. This unequal stress distribution cable we need to make it equal. So in a cable having homogeneous insulation, the maximum voltage which can be safely applied to the cable is limited to electrostatic stress at the conductor surface. So the homogeneous G value is needed within the underground cable. So if a dielectric of high strength is used in a cable, then it is useful just over the conductor where the stress is maximum. But as go away from the conductor surface, the value of dielectric stress is decreased. So dielectric will be unnecessarily strong and expensive. So we can say the same point we are keep on discussing. Same, to avoid the unnecessary expenditure in the making of manufacturing of cable, this unequal stresses we need to remove. So equalization of stress over the cable is needed. To overcome the above disadvantage, it is necessary to have a uniform stress distribution in the cable. So if you consider that cable, uniform stress, dielectric stress distribution is needed, so that we can make economical model of the underground cables. Process of achieving this uniform electrostatic stress is called grading of the cables. Is called the grading of the cables. What is the meaning of this grading of cable? To make equal electrostatic stress, uniform electrostatic stress within the underground cable, that making is called grading of the cables. By grading of the cables, we can make that dielectric stress equal. So today's lecture we discussed insulation of the resistance, which is given as Ri equal some formula we have seen, and capacitance of the single core cable, which is one more parameter of the underground cable, and dielectric stress G value. So these three parameters we have discussed in this class. So G is one of the important parameter in case of underground cables, and G value will not be equal within the underground cable. To make uniform stress in the cable, we need to go for grading of the cables. Next lecture we will discuss regarding the grading of the underground cables. Thank you.